So today I want to talk to you about declarative user interface in programming languages and specifically how we use them in Standard Charter. I'm going to show you a couple of iterations on the different libraries that we've been building over the years. And this is something that I'll take with you, the refinement process that we went through and how the library evolved into the way it looks like now. And the main driver of the design decisions that we took were performance and usability. So I'm going to be showing some use cases and how performance actually drove the design of the interfaces that we built. And the other thing that I would like to take with you is that declarative UI work in the real world. So we're using this in the bank for a lot of very complex applications. So it's something that is worth having. So let's start with a little bit of history. So I'm part of a strat team at Standard Charter, and we are part of a bigger team called the Modeling Analytic Group. We build software for different front office functions in corporate and investment banking. These are traders, sales, and structure functions. Among the things that we do, we develop a lot of graphical user interfaces for our customers, our internal customers, and they're all running on Windows. So we end up like writing applications in Windows too. We have our own compiler. Like Leonard was like one of the implementers of the new compiler that we have in house. And it's almost indistinguishable from Haskell. But yeah, it's our own compiler. It's a bit different from Haskell. So if you're interested into this language, there's a talk given by Morten, who is the head of Mac Markets, and in the Haskell Implementers Workshop in 2021. And there's a more recent paper on the proceedings of ACM on programming languages in 2024 that tells a little bit what struts do for the bank. This is a little bit of a timeline of the UI libraries that we've been building over the years. So it all started in 2010 with something called Widget. That was the first UI library that we built. And then in 2017, we started thinking about declarative UIs and how we can build graphical user interfaces better. Then after some initial internal talks and development, we found out that Virtual Widget wasn't particularly good at handling performance. So we came out with another Virtual Widget. We call it Virtual Widget 2. And that's the second iteration of the Virtual Widget library. The API was rewritten to some extent, but most importantly, the internals of the library were mainly rewritten. And around 2023, there was a lot of work done in terms of performance and usability. And at that time is where we saw that we're starting heavily relying on this new framework to build graphical user interfaces. So let's start from the beginning. That is where the widget library is the first iteration that we have to build graphical user interfaces. So it all started in 2010, and the main driver for having a widget library was because a lot of calculations and stuff were done on spreadsheet. And spreadsheets, they were really hard to maintain. Traders will commit the spreadsheet, to a central repository. It was very few controls, and they would share spreadsheet across emails. So it was a need to actually move into a more sustainable approach, and that's where widget started. Widget uses Windows Presentation Foundation. Remember that our users are all on Windows, and we are on Windows too. We have a thin layer of F# that exposes Windows Presentation Foundation to the MU runtime, and we have a layer on top of that basically works, exposes two things mainly: properties and controls. Properties, you can think of properties as mutable variables. You can initialize a property by giving an initial value, and then you get a property. You can update the property by putting a new value to the property. That will raise an event. It will tell whoever registered to that property that a new value on that property now is in place. You can register to events with the += operator, and for that you need a property and you need a function that will receive the new value of the property, and then you can do something about it. You can compose property too. And then widgets is built on top of properties. So a label, for example, it will be a piece of string they display on the user interface. And the way you create that is you give an initial value, and then that returns your control. And the control has a graphical representation, but it also exposes an underlying property. And in this case, the property is a string. And the way that you will change the label is by updating the underlying value of the property. Text box is almost the same. Take a look at the type, it's almost the same. The only difference is that text box will have a different representation on the UI. So you can input things in the text box, where with labels you can't. Button is slightly different. So you have a read-only property that doesn't give you anything. This is because the main thing that you want to do with buttons is to register for callbacks when the user clicks a button. And then you can compose controls too. This is how an application would have looked like in 2010. This is a very simple application. You have a text box and a label, and then you register for an event when the text box changed. And what you end up doing is basically putting the new value of the text box into the label. You can see it at work here. You start with type here, and then you change to hello world, and that will update the label. So this is pretty neat, easy to read, very good. And a lot of applications were built using this framework. But there are several problems with the widget library. The main problem really comes from the fact that you start defining properties and widgets, and then you start linking them together, effectively creating a big dependency graph, an implicit dependency graph in the whole application. You can have things like diamonds, for example. In this case, you have property 1, 2, 3, and 4. When property 1 changes, you update the value of property 2 and 3. And when each of these change, you update the value of property 4. Now, what ends up happening is when you update property 1, you get 2 updates on property 4. And sometimes you cannot control how this update happens. So it can be coming from the P2 or the P3 path. So when there's a bug that is related to this type of things, it's really hard to debug in actual applications. But then you can also have cycles, and this is an example of where do you want to have a cycle in the application, right? So we have an application that converts Celsius to Fahrenheit and vice versa. We have 2 input boxes, one for Celsius, one for Fahrenheit. And when the Celsius get updated, we need to update the Fahrenheit. And when the Fahrenheit get updated, you need to update the Celsius. Now, if you change the Celsius box, then that will update the Fahrenheit box and trigger an event. And in itself will trigger an event in the Fahrenheit input box. And that will in turn call the input box to be updated as well, the one for Celsius. So you have like this kind of, you update one property, but then the other one gets updated, and then you update it again, the other one, and so on and so forth. We have things to control this, but sometimes it can get out of control, and you can have these kind of really problematic things in bigger applications. But what I'm trying to illustrate here is that sometimes cycles, you want them in your libraries, in your applications, sorry. So at this point we say, okay, there must be a better way to write applications because this really doesn't scale for big application. And, this is when we start thinking about declarative UIs. And what do we mean by declarative UIs? Well, I want a model that contains all the information that the application needs. Effectively, what we're doing here is we're moving all the implicit dependency graph into a single place. That is a model. And hopefully that is an actual data type that captures everything the application needs. We have a view that basically it only needs to care about how to display in the model. There's no business logic there. We just grab the model and display into view. And then we have an update. Well, the view also can raise messages, and those messages are going to be raised as the user interact with our application. And then finally, we have an update function. The update function is in charge of running things or updating the model, right? And then the update function can also raise further events that can be handled again by the loop in the event queue. The update function, we would like to not have any IO operation because there's a UI lock that we need to. When you update the model, then the model needs to be rendered into the UI, and in order to do that, we need to acquire something called like the UI lock. A lot of the UI frameworks, they have a UI lock. That means you want to write single-threaded into actual display. So entering the UI monad is extremely expensive because you need to acquire the UI lock, and then you need to do things sequentially or single-threaded. So we want to avoid that in the update function. This is how your application would look in 2017. So you have an app, you have a starting model. That's the model that your application starts with. You have a view. The view takes a model and returns a view. And the view can raise messages. And then you have an update function that, given a model and a message, it will produce a new model and some commands. That's how you can run further calculations. The way it works is when the user starts interacting with the application, a message is raised. We call update function with a current model and the message. We get a new model. We just pass the model to the view function and we have a new view, so we can display the new view to the user. And there are ways to commands you can do. You can use commands for sending more messages into the queue or for spawning calculations that eventually will do something with that information that they compute. But we now need to translate all the labels, buttons, and compositions into the new framework. So what we did was try to maintain as close as possible the current implementation in terms of types. But we are replacing the UI, control, prop, string, all that with just the view message. And then at this point, you don't really need to care about controllers or properties or anything. Everything, you know how things will get updated. So this is the application that I showed before, the Fahrenheit Celsius converter. Notice that we have a model that contains the two scales, messages for when each of the scale change. We still have the functions that translate from one scale to the other. And now the update function, what it needs to do is, well, when the Celsius change, you need to update the Celsius in the model. And then you need to convert the Celsius to Fahrenheit and update that out of the model too. And similarly for the Fahrenheit change. And the view now, it only needs to know how to display the model and how to raise messages. So it says, okay, I'm going to start with a double box that when changed, it needs to raise this message and then display the text Celsius, and similarly for Fahrenheit. Notice that in here, we don't have any loop. It's just that all the loops all disappear. It's just everything happens in the update function. So, okay, so this library looks pretty good. Let's see if it actually performs well in the real world. So we're going to start by having a model that contains two parts. The cheap part that is cheap to render, and the expensive part that would be something that is really intensive to, or complex to render, so it will take a lot of time. The view of this model will basically display the two things separately. We have views for that, view cheap and view expensive. One will be expensive and the other one will be cheap. We have the messages and the corresponding update function. So in order to do this more concrete, I'm going to say that the cheap part to display is a text box. That is a plain text box that just displays the text, right? So when the text changes, I just update that part of the model, and that's it. And the expensive part is an integer. Now, this integer is going to be really expensive to display because, first of all, it's controlled by the int box, but then it controls how many buttons would I be displaying. So in this case, if I set the number of buttons to 10,000, then what the UI will do is will actually draw the 10,000 buttons. And that is way more expensive than the cheap part. So we test this, and then when we modify the number of buttons, yeah, it takes some time to actually render. So that is expected. But when we go and modify the text, then it also takes a lot of time to render. And this is not what you would expect. You would expect, text is just a text, so it should be fairly fast to display. So at this point, what we do is we enable our profiler and we run the same experiment to see where are we spending our time. And we get with this. So this is a flame graph that will tell you all the function, the most relevant function calls that take our time. And the whole thing takes 6 seconds. And this is just the flame graph for us changing the text box, right? So we don't expect any buttons or any of that expensive part to be in here. But if you take a close look to this, you see kind of two towers. It's like the graph is split in two. The left-hand side is all about comparing labels and buttons. And this has to do with this big part of the UI that is responsible for displaying buttons. For the buttons, each button will have its own label. And we spend a lot of time there, but we're not modifying that part of the graph. On the right-hand side, you will see a lot of things that has to do with hashes. And I will explain shortly why hashes are here. But this point, is is pretty problematic because that means that if you have any component in your UI that is expensive to render, then every change will actually be expensive too. So what is the problem? So why do we see this performance issue? Well, for starters, view is just a function, right? So when you get a new model, the only thing that you can do with a view is just apply the function. And what the view does is basically we have a DOM that we display. It's like a big tree that is the one that we actually display to the user, and we have a virtual DOM. So the virtual DOM is what view gives us. So when a model changes, we pass a new model, we get a new DOM, and then what we try to do is to compare the virtual DOM that we have in memory with the actual DOM that we display to the user, and try to do as little as possible updates. So what we're going to do is we're going to hash the nodes in the DOM, and then we're comparing hashes. If the hash is equal, we don't need to update that part of the tree. But if the hashes are different, then that means that we need to go and update the actual DOM that we are displaying to the user. So this is problematic because now we do a lot of work about like building virtual DOMs, hashing and comparing, just to find out that we don't need to do anything in that part of the tree. So this is quite hard to optimize. So at this point, we decide, okay, virtual widget, very cool library, very good idea, but it doesn't really work for us. So we decide to go back to the drawing board. And we say, what if we slightly modify view so it's not a function anymore, but it's something that we can actually use to drive performance? Well, we started by saying view is the only thing that really is problematic here. The rest of the framework is okay. So what we did is we changed view in a way that is actually a node now. So instead of generating a virtual DOM and having a real DOM, what we do is that we actually build a tree of nodes, and each node will be responsible for deciding if they need to be updated or not. So there are two types of nodes effectively. You have pure nodes. Those are nodes that will never change. So they're like completely independent from the model. And you have, dynamic nodes. And those are nodes that can change if the model changes. And we represent this with the node data type. You have a pure control. That is a control that never changes. So you just always display. And then you have an update node. And the update node will have a value, which is a control that is being displayed at the moment, and a function that can potentially update that control. You obviously need the actual model. That is the new model that you get. But now the model will be specific to the actual node. We'll see an example shortly. Okay. But what can I do with views? When the view was a function, then it was easy. I can compose it, I can evaluate it, blah, blah. Well, with this new view, it's just a node, like how we compose, how we do things with this view. Well, luckily, view model is a functor. So you can actually fmap over a view. And how does this work? Well, you have a function that converts messages of type 1 into messages of type 2. Those are the messages that are raised by the different views. And then you can convert a view model message 1 into a view model message 2. So it's pretty cool. How can we use it actually? Well, if you imagine a big application, and then let's assume that some part of the application is in charge of displaying, customer details, and we have a customer detail view or customer detail tab that is a view that displays the customer information, and it works on a model, and it produces customer detail messages. How do we integrate this tab, this smaller view, into a bigger model, into a bigger application? Well, let's assume that we have a model that is a model of the whole application, and we have a main view that is a view over model and message. But we cannot really use customer detail type because it's a view on model and customer detail message. But because views are functors, what we can do is we can fmap over the customer detail tab. And the type that I need is the function that I need has the type customer detail message into message. And this is just a new entry in the sum data type of message, right? So we're just gonna be effectively wrapping the customer detail message into the bigger application message. Okay, this is pretty cool. I mean, I can compose applications now. What else can I do with views? Well, views are also kind of contravariant in the sense that, so contravariant is, it goes the other way around like functors. So it takes a function from A to B and can take it from f of B to f of A. So views are almost contravariant in the sense that I would like to write something like this, instance contravariant view something message. And that something is where I want to apply the contravariant function or the function that I pass to contramap. And what effectively we'll be doing is we will focusing on the model. So before with functor, we were lifting a message into the realm of the bigger application. Now with contramap, what I will like to do is to actually focus from the main application down into a specific model. And I don't think that we can actually write this in Haskell, maybe with some crazy extension, but, what we have is instead we have a prof functor, and prof functor basically does two things. It gives us fmap and contramap. So it gives us, if I remember this correctly, fmap is, rmap. So it's basically f mapping on the second, type variable of the prof functor, and lmap is the other one, just like allow us to use contramap in the covariant position of the functor. Okay. So now we have views that are prof functors. We can compose applications even better because now my customer detail tab can only deal with customer detail model instead of the whole big model. And I can embed this nicely with using like the fact that views are prof functors by using rmap on the message and lmap on the customer detail tab. So if you see customer detail view, only concerned about customer detail model and customer detail message. So I can put this into its own module, and the customer detail view doesn't need to know anything about the rest of the world. And I can combine it nicely in a maybe like umbrella application where I will have one model that contains customer detail as a part of that model, and then a message that will wrap things that will be raised by the customer detail view. And the only thing that I need to do is to rmap and lmap. So just to make this a little bit more visual, what we're doing here at the bottom, we are constructing a view or an application that works only with customer detail stuff, right? So we have customer detail model, customer detail message, and customer detail view. And I can use lmap and rmap to lift everything into a place where I can talk about models and messages. Those are like the bigger model and messages that I will have in my application. Okay, so this is how we can, I already was able to do this when views were functions, but what I'm trying to show here is that we are not losing much by actually wrapping, changing the type of view. And we'll see that we can improve performance with this new model. So in order to understand how we can improve performance, we need to take a look at the internals of virtual widget. So what do we actually do when we are translating virtual widget into actual widgets? I'm showing here an example. The model is just an int. There is a button. When you click the button, the integer, I add 1 to the integer, and then I'm displaying the actual integer and with the button that says click me. So the tree will look something like that. You are composing two branches. One is a label that displays the actual integer, and the other one is a button that contains a label. Okay. So how does this get translated? Well, let's start with the left-hand side, and that is a label. And that label displays the integer. So that is model dependent. So you will need that to be a dynamic model. Okay? How does this look like? Well, we start with a simple value, right? So value will be a control, and the control will be something that displays the actual integer. And we have an update function. And the other function, what it does is, well, when the new integer is in the model, then I will show it and put it in the controller, right? So this is pretty simple. So it doesn't do any check. It's just like, every time that the model change, I just update it. But it doesn't need to be that simple. You can do something like, I don't know, maybe you can have a need update function that tells you if you actually need to update the controller or not, and then update it only if you need to, right? So there are like multiple implementations for this dynamic node in particular. Notice that this last implementation that I'm showing you here is something like we used to do with Virtual Widget 1, in the sense that we are not always updating the model. We're just checking if we need to actually update the control. But it's slightly different. So now in Virtual Widget 1, we need to compute the whole DOM and compare the hashes. So that is comparing the output of the view function. But what we're doing here is we are comparing the input of the update function. And we can do much more clever things with that. First of all, we don't need to do any work if we don't need to update anything, because we just compare the input. And yeah, secondly, a lot of times it's just like a quality check, which is like much cheaper than computing the whole DOM and hashing. Okay, let's take a look at the other part of the tree. Well, this is pretty simple. So you have like a label that says click me, and that never changes because it's always display click me. So that gets translated into a pure node that says label click me. That's fairly easy. Notice that there are two labels at play here. You have the green label and the blue label. The green label lives in Virtual Widget 2, and the blue label lives in widget. And this is how everything in Virtual Widget 2 get eventually translated to actual widget. And then we have a button that wraps that label. The button is also a static node, because we don't need to update the button. It's always raise the same message. So that's it. That gets translated to a pure node, which wraps a pure label. Okay, so we think that we maybe nailed it. So we're going to go and test it again with our example with previous example, and see how this performs. So again, this is how the example looked before. This is Virtual Widget 1. And then I'm going to change it to Virtual Widget 2. Notice that very little changed. Specifically, the view changed because the views are different. Now, instead of having a function, I have this view that is a profunctor. And then the model, I apply I don't get the model anymore. And I cannot apply the subpart of the model anymore to the other views. What I need to do is to use lmap, to do that. But there's nothing else changed. So this is the only change that we need to do. So we go again and we repeat the experiment. We enable profiler, we change text, and this is what we get. Okay. So we went from 6 seconds to half a second, with this change on the framework. So that's pretty cool. But still a lot of function calls, still like 420,000 function calls. And some of these calls, they have to do with some buttons as well and some labels. But I don't expect that. I really don't want to be dealing with anything that has to do with buttons and labels, because I'm just modifying. Remember, we're just modifying the text box. So can we do better? Well, actually we can do better. So we're going to introduce something that's called memoization. And memoization is a way to tell, okay, this view, we're going to show seek with this view if the models are the same. And what is the type of memoize? Well, you need to have something that can be memoizable and an equity function on the model. An equity class constraint on model. Luckily, views are memoizable. So we only need to have equality on the model. Right. So then with this change, we go to the profiler again and we generate a new flame graph. And this is what we have now. So we go from 6 seconds to half a second to 0.02 seconds and only 146 function calls. And this is almost the type of profile that you will see if you will be profiling an actual widget application. So I guess at this point, what I'm trying to show is that we managed to accomplish declarative UIs, but with the performance of widgets, which I think is pretty amazing. So I want to talk now about handlers. And these handlers, they were not driven by performance, but they were driven by the ergonomics of the application, of the library, sorry. So a lot of times you want to, when you have like a long running work, what you want to do is you start your work and then you inform the user that, you are doing some work. Otherwise they get really impatient. So how can you implement this using Virtual Widget 2? Well, you can split your work into 3 works, for example. You have work 1, work 2, work 3. You have messages. You need a message every time that you want to use to update the UI. So every time that you want to display something different to the user, you need to raise a message and handle that message. So what we do is we start the work. We show the user that the work started. We do some progress. We work. We raise the some progress event. And then we update the message to the user and we do a bit more work, raise another message, update the user again, do a little bit more work, and then complete, and that's it, right? But this can get out of control quite easily because you end up having a lot of messages just to update the user what's going on. Can we do better? Well, let's take a look at what command does, because command is what we end up raising in the update function. So command is a way to actually decide if you want to do an UI action or an IO action. Remember that entering the UI is expensive, so we want to differentiate this type of action. So you want to say, if this is an IO action, I can run it straight away. If this is a UI action, maybe I want to wait a little bit to see if there's another UI action because I need to acquire the log and do stuff. But there's no way to modify the model in a command, right? So we cannot really use the command for this. What we really want is update to have, instead of taking the current model and the new message and returning the new model and a command, what we really want to do is to have an update M type of thing where, I get the old model, I get the message, and then I'm in a monadic calculation that will return, actually that should be the model, that returns a new model. And I want that to be, the model is part of the monad state. So I want to have access to the model so I can change the model in a monadic calculation. And then I also want to be able to run IO actions. Okay. So what we do is we go and implement this. So we implemented this new type handler, and the handler, is a functor, an applicative, a monad IO, but it also implements monad state. So that means that I can get access to the model now, update it as I am doing the work, and no need to raise all these messages, right? And these are like how you can define handlers. So you can write an IO calculation in a handler, you can fork a handler, or you can send an alert to the user. So we go and rewrite the previous application, and now we only need one message. That is when the work starts. So we start the work. We still need to split the work into 3 chunks, right? Because we wanted to do some work, like tell the user we're doing some work, then doing the work, and then tell the user we're doing more work, and so on. Okay. So that's what we do actually. So we start work, we just inform the user about changing the underlying model, assign else status, which is a way to modify the model in context. And then we keep on triggering work asynchronously. Now, notice that this on the right-hand side is I think it's way more readable. It's all linear. You don't need to know about all these messages that are raised and handled all the time. So it's much easier to reason about programs this way. Now, a few notes about handlers. They don't really change any of the fundamentals of Virtual Widget 2, right? So it's a completely kind of different things than the move from a view, from a function to a profunctor. It's more about the building better ergonomics for programmers on how to define graphical user interfaces. It is somehow orthogonal to Virtual Widget 2 in the sense that we could have implemented this in Virtual Widget 1, but I guess we never did because Virtual Widget 1 was never used fully. Another nice thing is that now the messages only comes from the view. You cannot raise messages anymore. You cannot raise messages anymore from the update function. You handle just stuff on the update function, but you cannot raise messages anymore from the update function, which makes reasoning a little bit easier with these applications. And then handlers can compose much easily. And this is because they are monadic calculation, right? So you can compose them quite easily. Okay, so that's, I'm going to finish with some closing remarks, and how do we use this framework, Virtual Widget 2 nowadays? So we started in around 2019 with only 5, small applications, and now we have hundreds. Well, I think at this point we have more than 100 internal applications using this framework. Some of them are small, some of them are quite big. Here on the right-hand side, I'm showing you, something that is Cortex Live. Is a state-of-the-art intraday risk platform. So, traders will be having this on their computers, seeing their actual, intraday, risk profile. This is a massive application with a lot of ticking data, connecting to multiple services and having a lot of, submodels and composing those submodels nicely. As I say, the memory performance improvements were mainly driven by need. The changes in the API were mainly driven by the need of performance improvement. And at this point, Virtual Widget 2 is considered like the go-to framework to building a graphical user interface. So thank you for your time. This is all I wanted to talk about. And then I'm here if you have any questions.